Hey, yes, sure. We can start. I'm okay. I was checking on a couple of other speakers. Okay, so let's see this here and here and here. Sorry. Okay, so I think you can see my screen. So this is a program. Gregory was showing it a little bit earlier. So first, thank you for taking part in this parallel session. As we said, today there will be only 4 talks because Mukul is sick. So as a result, we will have plenty of time for the talks and also for questions. So I hope it will be interactive. And then I will ask you to mute yourself during the presentations, and at the end for the questions, and you can unmute in, say, orderly fashion. Okay, so welcome everybody, and the first speaker is Asaf Sper, who is going to present the state of the art of prompt emission, theoretical understanding, and some observational facts of GRBs prompt phase. Okay. So Asaf.
I cannot share my screen.
Yeah, I need to stop. And now you should be able to.
Now I can share my screen. I think it's this one. Can you see my screen now?
Yes, I can see your screen. Yes, absolutely.
Okay, let's see how to do it. Okay, so the title is Understanding GRB Prompt Emission. Where do we stand? So I made it kind of general based on the request, and there is a list of collaborators who might speak about the works. Zeynep, Damian, and Husna, which are here. David Eichler, as you know, just passed away a few weeks ago, unfortunately. Yang Li, Felix Wright, of course, Vidushi Sharma, and Mukesh Vyas that work with me. So the outline, right? So of course the problem, I'm going to look at take a side back in a sense. You know, it's very nice that to have a whole session devoted to a photospheric emission. This is something which we did not have a few years ago because it was much less, you know, popular, I would say. So I want to take a step back and saying, okay, what is the problem? Understanding what we see, and then look carefully at the data to see what does the data really tell us as far as the spectrum and the light curve. Then I will speak about the broadening mechanisms of the Planck function, the Planck spectrum, polarization, and then a new idea of that we're promoting in the last year or so. Let's see, is that working? Yeah, here it is. So what do we see? Well, this is something which we're all aware of. I just try to summarize everything within one slide. So the spectra, the key features that are common to all GRBs are the sub-MeV peak, the steep low energy spectral slope. In some bursts, not all of them, there is this emission that extends to very high energies from GeV to TeV, and there is a multiple components in the spectra that sometimes can be seen. By the way, can you see my mouse?
Yes, absolutely.
Okay, so I can use the mouse to point things. And then the light curve, of course, shows the variability. There is a distinguished prompt emission. You have to wait. I have a little bit of a problem with that's when I have to move it up. I'm sorry for that. There is a distinct prompt emission here. No, it's not so. How can I remove the? Oh, there it is. That's fine. Sorry for that. There is a distinct, you know, prompt phase with the afterglow phase. In many bursts, we're seeing X-ray plateaus, followed by a decaying afterglow. And then there are 2 additions which I added up, and that is the connection to supernova, which is well known, and relatively recently, the gravitational wave sources. So the basic picture, which is surprisingly hasn't really changed for many years, is you know, the fireball. I don't want to insult everybody, but I'm treating it like a very general picture, meaning that there is a gravitational energy release, rapid, which ends up in an explosion, resulting in a relativistic expansion that at the second stage have some dissipation of the kinetic energy that leads to the radiation that we're observing. When you look at it, then at least the original version was there, and you know, very nicely explains the key features which I put with V marks, the sub-MeV peak, the variability in the light curve, and the decaying afterglow. But the decaying afterglow came out as a prediction of the model, it is consistent with everything else, but it's not part of the model. And that's an important thing because there are a lot of details which are uncertain. And that leads to the big questions which we want a model to, why are we doing all that? And the big questions which the model by itself does not answer, we need to rely on other things, are one, the nature of the progenitor, and then the mechanism for jet launching, the composition of the jet, and the importance of magnetic field in it, which is of course related to the jet launching mechanism. And then to the next point, which is the structure, dynamics, and evolution of these jets. And then, of course, the nature of the dissipation mechanism, the nature of the radiative processes, which is a big debate. And then comes the connection of gamma ray bursts and other objects of interest, such as the stellar evolution, star formation, host galaxies, POP3 stars, supernova, binary gravitational waves, cosmic rays, neutrinos, etc., etc. And then the final point of interest is the relation, the association of gamma ray bursts with the basic physics, such as cosmology, Lorentz correlation, many other things. The clear point, the takeaway message is that this model, as a model, is incomplete because this basic picture is good in explaining some key parts of what we're observing, but it does not explain the many key questions that we're interested in addressing, such as the nature of the progenitor, the jet launching process, the dynamics, shape, and composition of the jet, the dissipation mechanism, and the radiation processes. Of course, the essence is that we're mainly seeing photons, so this is why we have this green arrow here. And so we have to deduce all the rest. So a lot of the models are either focused on the radiation or focused on the jet dynamic, from which they try to associate the radiation. There is some noise there. I'm not supposed to mute myself. Right. Okay. Just hold on. Right. The important thing is that as a model, the model is incomplete. Now, there is some misconception that some people are using, such as, using a synchrotron model. Well, synchrotron is not a model, right? It's a radiative process. When I speak of a model, I speak of the entire, picture, essentially. From the start, from the nature of the progenitors, throughout what happens all the way until we end up with the radiation that we're seeing. Now, since most of what we see come from the radiative processes, then what are the leading radiative processes? And I pointed out three, which has been thoroughly discussed. So the first one is, of course, the synchrotron, which is possibly accompanied by synchrotron self-Compton. The advantage is that it's ubiquitous in astrophysics. We see it all over. We understand it very well, right? Since the 1960s, it's seen in the afterglow. It's pretty clear. The requirement from a synchrotron is basically two requirements: to have energetic electrons, which means that there must be some sort of a dissipation mechanism that energizes the electrons, and a strong magnetic field. The second one is hadronic, mainly protons via proton synchrotron, or possibly any other model. The advantage is that we have direct evidence for its existence because we are seeing cosmic rays. So we know that somewhere out there, there is something that accelerates protons. And again, the requirements are energetic protons and magnetic fields. Now for the photosphere, the advantage is that it naturally exists in expanding flows, and it's an inherent part of the fireball model. And the third advantage is that can be extremely highly efficient. It can solve the efficiency problem. And this is something which we have noted like 15 years ago or so with some papers. And recently it's also been doing pretty high in the news, I would say. The requirements are essentially that there is a region of high enough optical depth to enable thermalization. And in addition, that we want to avoid adiabatic losses, which will reduce the signal. That is to say that the photospheric radius cannot be, if we look at the standard dynamics of the fireball model, there is an acceleration phase and then there is a coasting phase, and it cannot be too far in the coasting phase because then we're simply losing the signal. The temperature and the luminosity drops down simply by adiabatically. So what does the data tell us? When we look at the spectrum, The initial suspect was synchrotron, and it was indeed in the 1990s, this was the leading radiative mechanism, Mezaros et al., Tavani et al. The two key features are the location of the peak energy, the sub-MeV peak, which matches what we're observing. But then there is a low energy spectral slopes, which seems to be too steep, and that caused by the end of the 90s to pretty much abandon this idea based on what's called synchrotron line of death. Now, recent work show that maybe it is not too steep. If we're redoing the analysis, maybe it can actually be consistent. That's the work by Michael Burgess et al., which I believe Michael will speak about that in his talk. But as I said, this is not enough, because when you go beyond that and you say, okay, if I want to take that, by the way, Michael is not the only one. Of course, there are other people, the Italian group by Oganessian and Ravasio, which also published in this direction. The main problem, of course, is that when you look what it requires physically, then it requires magnetic fields of the order of a Gauss, but at a radius of something like 10 to the 17 centimeters. And when this translates to physical conditions, that means that the ratio of energy to ambient density, units of 10 to 53 and 1, that is greater than 10 to the 7, as opposed to something of the order of unity. Which is inconsistent with what we know from many objects from interstellar medium. There are alternatives such as the jet within jet model, but again, we're not really sure how this works. There is no clear picture here. There is no dynamical model. So I would say this is less appealing. In order to solve this problem, there was a recent suggestion. Well, it's not so recent again. This is something which has been there in the literature for a while. And recently became more interesting. People became more interested in that, about the proton contribution. The proton cools down slower, so they require that can occur at a much smaller radii of something of the order of 10 to the 13 centimeters, with magnetic field of 10 to the 6 Gauss, which is much more what we'd expect them to be. But then again, this model has some theoretical problems, because it requires that there is too much energy getting to the protons, more than the kinetic energy, which means that there is something which we do not understand in the acceleration process. And this is basically the background that leads us to the photospheric emission. Now, before discussing the photospheric directly, more than 10 years ago, there is this event which many people view as the Rosetta Stone. This is GRB 090902b, which shows spectrum which was extremely steep, so steep that it required it to be thermal emission. But the other very interesting feature of that burst, beside being so narrow, is that it was a long burst which lasts a few tens of seconds. And we could see that the spectrum itself, which was initially narrow, opened up in time. And that pointed out to two things, right? It pointed out to the use of the need to use a time resolved spectroscopy in order to identify the data. And it also showed that something might be changing during the pulses and, of course, during the bursts. When we now can combine, we have 10 years later or 12 years later, that's a work by that was led by Lee, which I believe will speak about that later on, either today or tomorrow, or the next time we have this session, which looked at the multiple pulses. And when we look at multiple pulses, we're seeing, and when we do this time result spectroscopy, we're actually seeing that both the spectral slope, what we call alpha, and E peak, both of them vary within the pulses. And the general trend, which I'm not sure it's easy to spot from here, is that the spectral slope becomes softer with time, which means that the harder spectra occurs earlier. And this is a possible indication for a change in the radiative process. For example, we may be starting with a synchrotron we may be starting with a photosphere and then may turn into a synchrotron later on. Now, the next question is, okay, so if we accept that there is a photosphere, then what are we actually going to see? And it turns out that this is not such a trivial question to answer. The simplest case that we can think of is what's called a pure Planck. So there is nothing that interferes with a pure Planck. It's what we call the non-dissipative photosphere. Other people call it NDP. Now, of course, Planck is something which you learn in textbooks, and how it looks like, what would be the Rayleigh Jeans part of the spectrum. But since the more than 10 years ago, people, including myself, started to look at the aberration of light. And in fact, Andrei Belobordov showed in a very nice paper that the spectral slope, the low energy spectral slope, should be more like a 0.4 rather than 1, and this is the NE, so 1.4 if you're looking at the flux. But it turned out that even that is not what we expect to be observed. And the reason is that the detector that we have is limited in an energy band. If you look, the energy range here is quite long, but the detector we have is always limited to 2 or 3 orders of magnitude. So when you are taking the limited, typically GBM energy band, we find out that the spectral slope actually depends on the location of the peak relative to the window which is being observed. So this is a very nice work which was led by Zeynep Akunir, a student of Felix Wright, my colleague, which shows what alpha should really look like. So it's actually much less steep than it is, than one might naively expect. And once we understand that, then we can ask ourselves, what is the fraction of gamma ray bursts that show evidence for photospheric emission? And what we say, this is the first work that was led by Akunir, that when we look at the sample of long bursts, and there is a lot of selections here in picking up those data which are have a good enough qualities, signal to noise ratio of more than 20, etc., and doing, of course, a time resolved spectroscopy in order to identify the steeper spectral slopes, one finds that 1/4 of the long GRBs are actually consistent with being above this NDP line. So consistent with having a pure photospheric origin without any, you can say, contamination or anything else that might happen to this spectra that could modify the spectra. And then in a subsequent paper led by Husna Dereli Begue, we find out that when we look at the short GRBs, this fraction is actually larger. It goes up to 36%. So more than 1/3 of the pulses that are being observed in short GRBs within the GBM catalog are consistent with having a pure thermal origin. Now, when you look at only those bursts, I'm giving you now a little bit of head up towards the talk that I believe Husna will be talking about. You find out some very interesting things which are pretty much obscured when you look at the entire sample of short GRBs. For example, you're seeing that there is a bimodal distribution in the peak energies, which can correspond, when you analyze the data properly, could correspond to a bimodal distribution in the Lorentz factor. And in fact, if you look here, you find that this is the T90 duration. So the black dots here are the short GRBs which are above this NDP line, namely consistent with having pure thermal origin. And you find that there are two groups. The red ones are the ones that are not consistent with this NDP line. So it's kind of smeared up. Normally you would say this is the short burst, right? Just based on the T90. But when you look at the T90 and the hardness ratio, and you make this selection, you find out that there is a clear distinction here, which may point out that short GRBs population, what we call, are actually made of two separate populations, which shouldn't be really surprising in some sense. So it might be a continuation of what we call the long GRBs, which are around here. So it's, when you do this, you can get to quite interesting results. I'll let, this is kind of a promotion to the talk that will be given tomorrow. I believe tomorrow. Now, if you get that can give a very interesting application. For example, the Yoneto correlation, the correlation between the peak energy and the luminosity. Now, people have noticed that. This is a slide which was taken from Ito et al. 2019, essentially basically saying that maybe we can explain this correlation as simple viewing angle effect, right? The observed frequency is just Doppler boosted once. And just from Rybicki and Lightman, right, the luminosity should be proportional to I nu times nu, so it should go as nu squared. So you end up that if L prime over nu squared is invariant, then the observed luminosity should go as the observed frequency squared. And if you associate the observed frequency with the temperature, and that's the E peak, then you get that L goes as E peak square, which is exactly the Ionetuku relation. However, this is not as simple as one might think it is, because essentially this requires some intrinsic, there is some hidden assumption here, which is that intrinsically, the co-moving luminosity is proportional to the co-moving temperature square. And the co-moving temperature is varying along the jet because of the adiabatic losses above the saturation radius, which goes the photospheric radius to the -2/3. So essentially, this is something which we showed back in 2012. It can work, but there is a strong assumption, which is that the photospheric radius here should be constant, namely independent on anything else. Or in other words, that the Lorentz factor should depend on the intrinsic luminosity. Can this work out? Maybe, but it requires that the photospheric radius is fixed. Is it something which is natural? Maybe. I don't want to say yes or no here. I say okay, it may be related to the stellar size, maybe related to the cocoon, maybe related to something, but there is something in here which needs to be thought of properly. And I believe that Ito, when he gives a talk, we'll discuss that. Now, this was the simplest model, but we know life is not as simple as they may look like. So the next complication is, of course, that we just assume that there is no dissipation, or the photosphere is just a pure photosphere, right? The NDP, no, non-dissipative. But what if there is energy dissipation below the photosphere, right? Which we do have a dissipative photosphere. Now, this is something which people have noticed, for something like 20 years. This is a result from Zhang et al. From 2003. And then later on down the line, there are many other people who worked on that. Miguel Allo, Zhang, Mizuta, Lazzati. This is Lazzati's group from 2013. There are much newer results by Or Gottlieb, who will speak after me, that will show how there are some dissipations. So, there is some dissipation. There is some friction. The jets are not just floating in vacuum. They're floating inside stars, so obviously there will be some energy dissipation, and this energy dissipation will lead to subphotospheric energy dissipation, which will lead to conversion of kinetic energy into radiation. Below the photosphere, there will be subphotospheric dissipation, which will lead to radiative mediated shocks. And above it will be dissipation in optically thin regions, which essentially will end up with collisionless shocks. Now, it turned out that this scenario is something which has been investigated also for quite some time now, something like 15 years or so since we published this paper back in 2006. And, along the way, there has been several other papers, many other works that I just put two, but there are others by Wurm et al. And Ito et al. That considered the outcome of such a scenario. What happens when we're going to have a subphotospheric dissipation? Basically, what will happen is, of course, that you end up with a broadening of the photospheric signal, right? What will happen is that regardless of what, the details of the microphysics of subphotospheric radiative mediated shocks, they will hit the plasma. Now, the electrons will end up, and this is something which we showed a long time ago, we'll get a quasi-steady state because there will be very rapid heating, which is followed by very rapid radiative cooling of the electrons. And therefore, the plasma will be characterized by two temperatures, an electron temperature and a photon temperature, with the electron temperature naturally being higher because the dissipation gives its energy to the electrons. And so the resulting spectrum will depend mainly on two things. Will depend on the optical depth, namely how many scatterings we can go. And also it will depend on the ratio, how much energy we are giving to the electrons, normalized to the thermal energy of the photons. And we might end up with something that looks any of these plots. This plot, by the way, was assuming continuous heating. So there was not even an assumption of acceleration, which may not exist in subphotospheric dissipation, just heating of the particles. So we might see this kind of a strangely looking shape of, synchrotron peak, and then there'll be like a thermal peak, and then of course there'll be quantization of them. The end result, of course, as you go to higher and higher optical depths, you end up with a multiple inverse Compton scattering becomes more and more important. At the end of the day, it broadens the thermal peak. And if you go to extremely high optical depth, so namely you're assuming that the dissipation occurs very deep in the flow, then you end up with, rethermalizing again your particle now with a new temperature because you give them some temperature. The main problem with this model is that there is no strong predictivity, right? Because no theory or simulation gives you a very good prediction of the location of the dissipation, namely of the optical depth. Of course, simulations show you something, but I believe that they are very sensitive to the initial conditions that you put in. So it's, and obviously simulations will just complicate things in many ways because you have dissipation that occurs in several ways along the jet. But it's there. I mean, you end up with something which is quite, complicated. The other thing is this geometrical effect, right? When you have a relativistically expanding plasma, then obviously the photosphere is angle dependent, which is very easy to see because photons that are emitted on the line of sight have to go through a shorter path or interact with less particles than photons that are emitted from the same radius, but from a higher angle. And you can show how the photosphere looks like. It's actually a very nice exercise to show that the photosphere as a function of the angle would go as theta over sine theta minus beta if you're assuming that there is a continuous outflow at constant velocity beta. But when you think of it a little bit more, you end up that, if you define the photosphere as the last scattering surface of photons, then these are pretty much vague. So you have this vague photosphere because by assumption, there are particles everywhere, so photons can be scattered everywhere. And you can describe them by probability density function. And that, of course, leads to broadening of the naively expected signal. But this is a too simple model. This is a pretty simple model we wrote down in 2008. But then we thought a little bit more about that. And at that time, there were already these simulations that show that actually the Lorentz factor, it's not a spherical explosion. There is some sort of a jet-like. And when we say jet, that means that the Lorentz factor has some angular dependence. It depends on the angle. And so based on this simulation, we just wrote down a toy model, which essentially says that the jet has some opening angle and then it just goes down. So gamma theta goes as gamma 0 and then divided by 1 over theta jet with some power law p, which determines how steep the jet decays, right? So when p goes to infinity, we have this stop hat jet, but this is not the reality. And so really we have in this type of model, we have three parameters that describe the jet, which is, the Lorentz factor, the jet opening angle and the power law. And there is a fourth parameter, which is the viewing angle, which is which affects what we're going to see. And essentially what we're going to see is extended emission from higher angles, from angles that are higher angles to the line of sight, which in another word of saying it's a relativistic, this is the relativistic version of the limb darkening effect. What it will give when we look at the emission from the photosphere is something that might look something like that. This is divided into three parts. There is this inner jet where the Lorentz factor is roughly constant. There is this outer jet, which of course will contribute to lower energies. And there is this, what we call envelope, which will contribute maybe to the radii. Of course, that depends on how the luminosity is as a function of angle. So we end up with something that does not resemble at all, a Planck in a way. It turns out that this is not particularly sensitive to the different viewing angles that one may have. It does affect somewhat the peak, but not too much. The result, it turned up to be quite robust. We end up with a pretty flat spectrum, which is entirely due to the emission from the photosphere. There's no synchronous radiation here. There's just comptonization. There's not even sub photospheric dissipation, just comptonization in the structure jet. Another very interesting feature of the same idea is polarization, right? Obviously, we know that scattering produces a linearly polarized light, but in order to see the polarization, we need to somehow break the isotropy. So a necessary condition is that the photon field being anisotropic, which is exactly what we see near the photosphere. So we can, in principle, seeing emission, which is at angle of 1 over gamma, which should be 100% polarized. Now, of course, the problem is that if we're sitting exactly on axis, we see nothing. But it's just more likely that we sit somewhere off axis, just a phase space effect, which means that what we should actually see would be somewhat less in luminosity, but much higher in polarization. So when the observer is off, slightly off axis, this breaks the rotational symmetry and end up with the polarized signal. And that's what we find, that the polarized signal, this is the Q parameter, Q over I, can go up as a function of the viewing angle up to 40%. Of course, we are losing flux. The red curve here is the flux by several orders of magnitude, but we can still get some quite substantial polarization for an off-axis observer up to 40%. This is a huge number. Never see, well, we did see actually, these tens of percent of polarization and still see a significant flux. And there is another natural prediction, which is a pi over 2, 90 degree shift in the polarization angle as we are moving away from the jet, or as the jet parameters vary. Of course, the spectra that we'd see accordingly would not look like a Planck at all. We see this extended emission from the shear layer, which will give us some flat spectra at high energies. There is another effect which I won't have time to touch, which will end up with some sort of a power law. Have we seen that? Well, the answer is possibly yes. In recent years, there is this, some new satellites which are sensitive for polarization. This is the AstroSat, and this is a GRB 160821A, which is very bright. And we actually saw it's very energetic, and we have seen polarization. And the really interesting thing about this particular one is that we actually saw polarization angle change of 90 degrees twice, which are associated with the peak and with the decay part. This is something which already published, and we're still having another paper on that, which is currently in preparation. We're still thinking of a clever way for continuing investigating in this direction. Finally, I want to describe a different idea. Maybe we got it all wrong. I mean, back a few years ago, David Eichler came with some idea of, again, based on these simulations, which show that we have this jet that drills away through the star, but maybe it doesn't go all the way. In which case, it will manage to produce this, cork, possibly made of cocoon material, so material from the star, etc., which is pretty much expected. And the cork would not be penetrated by the jet. So in this case, what we really have is that if we have a source of photons that come from the inner regions, which we may have, for example, due to annihilation of pairs, which may be produced there, then what we may see is that these photons penetrate this expanding cork from behind, or expanding cocoon from behind, and being backscattered. Now, because at a certain point, this cocoon will reach relativistic velocities, although they will be scattered from the back, unless they will be scattered directly from this, a small region which is shaded, which obscure it, an observer which sits slightly off axis will actually be able to observe them. This is a work that was led by Mukesh Vyas. So one paper was accepted. The second one is now in process of being accepted. And what you end up with has some very interesting features, because all of them are pretty much what we're observing. So we're seeing the spectral slope, which is consistent with what we have. Of course, the scattering from angles which are closer to the line of sight will end up with a higher Doppler boost. So we'll see that at higher energies, the light curve is pretty much consistent with what we have. And if the cork is hot, we also have contribution from the hot electrons, which will end up with a high energy tail, which is consistent with what we can get with what we're actually seeing with this high energy spectral slope that we're seeing. And for me, I guess the most interesting result is this one. We do get naturally this E-peak E-iso correlation, what's known the Amati correlation, as a viewing angle effect. And the nice thing is that, as opposed to the other models, we do not need to have any a priori assumption here. It's just automatically we get it. So I believe that Mukesh Vyas, I think, will be speaking. I don't know exactly. I don't remember exactly when. Will be will be devoting his talk to that. So I hope I'm not too much over time. I think okay.
No,
So
no, you are good.
to summarize, I just got to the summary slide. The takeaway message from this kind of starting talk. Photospheric emission is a leading. It's not unique, but it's a leading. I'm pretty convinced now that it plays a major role, but you know, it's not the only role. As a radiative process that shape what we're seeing during the GRB prompt emission, we have clear evidence for a change in the spectral shape during the prompt emission, during individual pulses, which indicate that there is more than a single radiative process. Possibly, you know, the conditions are changing. The spectra that we see does depend on the observed band, so it does not look at all like a Planck. It's polarized. We expect to see some polarization. It does provide us with the most natural explanation to the observed correlations, peak ISO, peak luminosity, etc. Of course, the importance is that the comptonization here plays a very major role. So synchrotron emission may be subdominant here in all these type of models. And you know, a different type of photosphere, the backscattering model, provides a natural explanation to this peak ISO, so-called the Amati relation. Okay, I think that's about what I have to say. So thank you very much for your attention.
Well, thank you, Asaf, for this very good talk, this very good summary of the situation in the field. So I hope you have questions for Asaf, and I'm sure he will be very happy to answer them. So please, if you have questions, unmute yourself and ask them. Don't be shy. Go ahead, Ito.
Hi, Asaf. Thank you for the very nice talk. Yeah, I have just one quick comment about my work you just introduced. So I think you made a very simple simple explanation how the Yonetoku relation arises from the simulation. Like you said that photosphere has to be constant or such like that, but actually the simulation shows a very structured shape for the jet. So the photosphere itself is highly angle dependent, and the Lorentz factor is angle dependent. So you know, such simple explanation can't be valid in our simulation. So I don't have a good, unfortunately, I don't have a good intuitive simple explanation for it. But yeah, simulation somehow predicts structured shape of the jet, which reproduces photospheric emissions that have a correlation, like Yonetoku relation, due to the viewing angle. Okay, this is just a quick comment about our work. Yeah.
So thank you very much. I'm looking forward to your talk. Again, as I say, at the end of the day, it will boil down. I checked it out. It will boil down that the photospheric radius needs to be fixed in some way. Now, maybe you get it naturally. Maybe this is something which I'm not ruling out the possibility that because you have these simulations, which show that you have a certain type of stars and there is a certain density profile, maybe you get this naturally. But it is there. I'm pretty sure it's there because otherwise you simply won't get it. You simply get that the scattering is too big. So I don't know. I think there is certainly a lot of place here to continue looking at that, because I think there might be something in there which we see and we don't yet fully understand, that I don't know. And I'll be definitely happy to continue look at that with you.
Okay, thank you. So yeah, again, just my comment is, photosphere is not highly angle dependent. So anyway, let's talk maybe after the session or something. Okay, thank you.
Okay, thank you for the comments, the questions. Merlin, please unmute yourself.
Yeah, you can hear me?
Yeah.
Yes, absolutely.
Good. Okay, thank you, Asaf, for the overview. I just had a question about the polarization.
Yeah.
So you mentioned this one GRB 160821A, where with the associated results in this paper, you found some higher polarization results, but all the other associated results give typically very high levels of polarization. Like the lowest I think they get is 50.
Yeah.
But that is not consistent with photospheric predictions, right?
No, I didn't say that. You get actually, I showed the opposite. I saw here in this particular case, you get polarization fraction of 30%.
Mm-hmm.
I actually showed here that, just from the photosphere, and again, we use a certain model which you can play with, right? I mean, I didn't say that necessarily. We use a toy model. That's the fun thing, right? We took some toy model. Nobody says that the toy model we took, that the Lorentz factor that we took necessarily looks like that. Well, we think this is a representative model, but we don't know. You can argue for other things.
So,
but with this representative model, we were able to show that you can get up to 40% polarization. This
yes.
Q, right? It's up to 40%. So tens of percents of polarization are possible. It's not something which are ruled out, while the luminosity is still while the burst is still quite bright. Right, you are losing, of course, when you're sitting offside. We're sitting offside, but you're not losing that much. You're losing, 2-3 orders of magnitude. That's a lot, of course, but it's still enough to keep you bright. So
this was a very bright GRB.
What?
Right,
yeah,
so,
I know. This is why I told you that we have a follow-up paper on that, which we still haven't published, because we realized that there is something unique happening here.
Okay. My point was more that there's the other 10 or so GRBs that were published by us, and they all consistently give high levels of polarization. And I would say that seems very unlikely then to come from these predictions, because all of them would have to be in an extreme off-axis case in that case.
Maybe that goes back to the question I said. This one is unique in many ways. I mean, you're saying that the time here, this one I know, so that's I can speak about, right? Because I was working on that one, right? The time of the pulsar is between 100 and 150 seconds. So it's very plausible that this is actually not a photospheric. This is not maybe even a prompt emission in some basic sense. Maybe there is some bright thing that happened later on. So yeah, I wouldn't rule out. I don't think there is any way of ruling out the fact that this actually may come from a synchrotron. But again, synchrotron has its own problems here, so it's not that clear what happens, I would say.
Okay,
but yeah, I would take this comment and I agree with it.
Okay, thank you for the question, Merlin. Is there other people who have questions?
I actually have one.
Yes, please go ahead.
I wanted to ask about this quark model that you mentioned and that you're also working on recently. So as you may know, in full 3D simulations, unlike simulations in 2D that you showed, don't support the presence of this quark. So I wonder what type of, or what set of parameters you need to assume in your model in order to be consistent with observations.
Again, I did not hear very well. There was some noise. Can you please repeat? You said that 3D, 3D simulations do not support something, but I did not get what exactly.
Okay, so the quark model is something that is not supported by 3D simulations. This has been shown to be a 2D artifact. And so the question was what parameters you need for the quark to have, in particular, for instance, the mass of the quark, in order for it to be consistent with observations of the prompt emission.
Okay, so I think there is a very large range of parameters. I cannot tell you right away, because what we have seen in simulations is, as far as I know, it's 3D, but don't take I haven't looked very carefully at that. If you have jets that are not that strong, they might not completely penetrate the quark. So you have these blobs that you're seeing that goes out of the stellar envelope, and then they can scatter back the radiation that may be coming from behind. Now, interestingly, and in the paper that was published that we published earlier this year, led by Vyas, it may actually be written here, we do not need a particularly high Lorentz factor. Maybe it's not written here. I think that the Lorentz factor that we used for these quark would be something of the order of 20 or so, something like that. So we do not need it as opposed to the classical GRBs in which the entire fireball moves at Lorentz factors of 100 or hundreds. Here we're talking about tens, roughly, and that is enough for us to to get a signal which is consistent with the signal that we're seeing. Okay, I hope this answers your question.
Yeah, thank you.
Okay, so we have like 1 more minute for a short question if there is. If not, then we will go to the next speaker, who is actually you, Ore. I think you have a small problem of microphone. I also have some problem to hear you. It's coming a little bit. Yeah.
Earphones.
Oh, you still have the problem. I mean, am I the only one to have the problem, or you also have problem to hear?
No,
or
it sounds like Bluetooth intermittency.
yes. Okay. Okay. So since there is no more questions, so let's thank Asaf for the very good presentation. Thank you, Asaf.
Thank you.
And let's listen to Ore. Please, the stage is yours.
So I hope it's better now.
Yes, it's much better. Yes, thank you.
Great. Okay. Okay. So first of all, I would like to thank the organizers for the invitation. And what I'm going to discuss is the prospects of inferring the jet launching mechanism from by using numerical simulations and calculating from these simulations the photospheric emission and compare it with observations and see whether we can place any constraints on the physical properties of the jets by this type of analysis. So I'm going to start with showing you a movie taken from a 3D simulation of a very simple jet, the simplest you can imagine. This is a hydrodynamic continuously long jet that is drilling through the stellar envelope. The color coding here is the isocontours of the proper velocity of the jet elements. So as the jet is breaching through the star, it forms the cocoon around it. The two co-evolve inside the star. And as the jet and the cocoon reach the stellar edge, they break out from the star. Roughly each element is expanding to an angle of 1 over the proper velocity of the element. And they form this jet cocoon structure that Asaf also showed in his talk. And this is what eventually would emit the radiation, maybe at the photosphere, maybe at different phases as well. And what we did in this work is we calculated semi-analytically from the output of the simulations the photospheric or other type of prompt emission, and we compare it with observations, and we saw how or whether they're consistent with each other. So in particular, what we looked into are some relatively common characteristics of the prompt emission, also discussed by Asaf. So one is the high efficiency. We know that GRBs prompt emission emit a substantial fraction of their energy during the prompt emission phase. So this is one thing that we need. Another thing that we examined is the variability in the light curve. We know that typical timescales of the variability that is a recurring feature in GRB light curves is of a few dozen of milliseconds. This is another thing that is required. And also the spectra. The spectra, we don't have a self-consistent calculation. I assume that Hirotaka and Tyler will discuss more detailed calculations with Monte Carlo of the spectra in their simulations. So what we did is only an order of magnitude estimate of the spectra, but I will also discuss this during the talk. But as I mentioned, we will focus on the first two. So the high efficiency of the prompt emission can be attributed either to photospheric emission, to internal shocks, to magnetic reconnection. We don't know what the mechanism is, but whatever the mechanism turns out to be, it would have to account for the high efficiency of the prompt emission. And it is tightly related to the magnetization of the jet. In the case of magnetic reconnection, it's straightforward. In the case of internal shocks and photospheric emission, I will also argue and show that the magnetization plays a huge role in determining the photospheric emission and the internal shocks. The other characteristic that we focused on is the rapid variability of the light curve. This can emerge either due to the central engine intermittency. So if the central engine is not working continuously, then it naturally leads to the emergence of a rapid variability of the light curve. Another possibility is that the jet is forming instabilities during its propagation in the dense medium, and these instabilities would later be translated to some variability of the light curve. And this again is related to the magnetization. The magnetization can tell us what type of jet launching mechanism is, and therefore it's related to the central engine activity. On the other hand, the magnetization can also lead to current-driven instabilities, or alternatively stabilize hydrodynamic-driven instabilities, and therefore it's also related to the variability of the light curve. So to summarize, the parameters that we focused on, the parameter space, is spanned by two parameters, the central engine activity. It can either be steady or intermittent. So this is one parameter that we examined, and the other one is the magnetization. The jet can be unmagnetized, mildly magnetized, or highly magnetized. And I would like to emphasize that when I say magnetization, what I'm referring to is that the magnetization of the jet following the collimation nozzle. And it will be more clear during the talk. We do not care specifically what the magnetization of the jet upon launching, but rather after it has been collimated, since there is some magnetic dissipation in the collimation nozzle, and therefore only the magnetization after the collimation would be the important magnetization for the prompt emission. So we basically performed simulations that span this parameter space and looked into the light curves that we find. So let's start with again the simplest form of jets, which is unmagnetized steady in central engine jets. And this is the picture that we see in 3D simulations. So the upper panel here shows the energy per baryon. The lower panel shows the mass density. Red colors are high, blue colors are low. And you can see that the jet is here, is propagating from left to right. So we have the jet forming a double shock structure at its head, following the collision with the stellar envelope. This leads to the formation of an outer cocoon and an inner cocoon. The two together compose what is known as the cocoon that collimates the jet. And this is the collimation shock that you can see at the base of the jet. So the collimation shock comes as a result of jet fluid elements encountering the cocoon and then deflected and converge back to the axis. And following the collimation nozzle, we have this diffusive structure of the jet that you can see here that comes as a result of the formation of instabilities. So what I will argue is that this collimation shock at the base of the jet is playing arguably the most important part of the jet in determining the characteristics of the prompt emission when we consider the photospheric emission. So let me start with the variability. So due to this lateral acceleration of the jet before it's converging back to the axis, we have basically heavy material pushing against light material. This leads to the formation of Rayleigh-Taylor instabilities on the jet cocoon interface. The Rayleigh-Taylor instabilities start to grow, and at the tip of the collimation shock, they, together with another type of instabilities, Riemann-Meshkov instabilities, lead to the disruption of the jet coherent structure and lead to this, to the emergence of this irregular structure of the jet, which at the photosphere would be translated to high and low efficiency or rapid variability of the light curve. So this is one effect that we see due to this lateral motion at the base of the jet. The other effect of the one thing that I can show is a head-on and edge-on video of the jet, and you can see here the growth of the instabilities on the jet cocoon interface, and following the convergence back to the axis, they take over together with this Riemann-Meshkov instability that exploded from the center, and then the jet starts sharing more and more of its energy with the cocoon, and therefore becomes irregular and support the existence of variability at the photosphere. So this is the first feature. The second feature is the efficiency. So efficiency, as Asaf mentioned, is something that can depends on the coasting radius and the photospheric radius. So the coasting radius is where the jet finished its acceleration, or the typical radius at which the jet converted its internal energy to kinetic. And the photosphere is where the photons can diffuse out to the observer. Now, if the coasting radius takes place before the photosphere, then it implies that by the time that the elements reach the photosphere, they have no internal energy to radiate away, and therefore the efficiency would be very low. If, on the other hand, the photosphere takes place below the coasting radius, the efficiency can be high, as the internal energy is still stored in the fluid elements and can be emitted. Now, what would determine where the photosphere is located with respect to the coasting radius? So here I would show you again that the collimation shock is the one responsible for the high efficiency. So let's first consider a case that there is no collimation shock. So the jet starts its conical expansion right from the size of the compact object, very deep inside the star. Since we know that the Lorentz factor of jets, of GRB jets, should be a few hundreds, maybe a few thousands even, it implies that the coasting radius, since the Lorentz factor scales by the Farabault equation linearly with the radius, would be much, much below the photosphere, and therefore the efficiency would be very low. If, however, we have a collimation shock, then what the collimation shock essentially does is converting back kinetic energy to thermal energy, and then we have a new origin, a new effective origin of the jet, from which point it starts its conical expansion once again, and this is the tip of the collimation shock. Since the collimation shock is taking place, as we see in simulations, at a radius of roughly 10% or 20% the size of the star, that means that the coasting radius would be pushed to radii that are comparable or even above the photosphere, allowing very high efficiency at the photosphere. And therefore, the collimation shock here also comes in handy for explaining the high efficiency. Now, if we consider for a moment the other type of continuously launched jets, which are jets with magnetization, then we see something very interesting, and this is by introducing magnetization as low as 1%. Sigma is the magnetization parameter representing the ratio between the magnetic to thermal energy. We see that the jet is already starting to feel the stabilization effect of the magnetic hoop stress, and this stabilizes the jet to the extent that it will show no variability in the photospheric emission. And this is something that can also be seen head-on and can also be seen in a movie similar to the one that I showed for the hydrojets. So here we have the instabilities on the jet-cocoon interface, but they never manage to penetrate all the way through to the spine of the jet, such that the spine remains intact. So this already gives us some very important difference between magnetized and hydrodynamic jets when we consider, again, a continuously launched jets. And this is that while both of them are highly efficient, and I will get back in a second to the SED peak, we get highly variable light curve from hydrodynamic jet, but no variable light curve from the magnetized jet. So this model can be ruled out based on this observation if we consider a continuously launched jet, just because they're entirely stable and there is nothing to induce the variability that is required in the light curve. As for the SED peak, as I mentioned before, I suppose that Hirotaka and Tyler will discuss it in more details, but I will just mention that since the collimation shock is a radiation-mediated mildly relativistic shock, we know that these type of shocks are subject to a phenomenon called pair production regulation, which is basically that the shock is too fast to allow a generation of sufficiently sufficiently high number of photons to share the energy of the shock. In this case, it becomes dominated by pairs, and free emission leads to the generation of photons that can regulate the jet back to a rest frame temperature of roughly 50 kilo-electron-volt. So this is a common feature of all the mildly relativistic radiation-mediated shocks. They're independent of the Lorentz factor, and they're always stabilized by pair production on rest frame temperature of 50 kilo-electron-volt. And then when we boost it to the observer frame, it will become a few hundred of kilo-electron-volt, which also is consistent with what we see in observations. And therefore, in this sense, this photospheric model is consistent also with this observable. We also get internal shocks, but they seem to be too weak to broaden the spectrum to this band power law of broken power law function. But this is again something that requires full calculations that maybe Rotaka and Tyler will discuss. And this is the light curve that we calculate by post-processing the simulation. You can see that we see both high variability and high efficiency, at least on axis. As we go already to 6 degrees out off of the axis, the efficiency drops substantially, and it's inconsistent with observations. So this is, to summarize the first part, if we consider a central engine that is steady, we can only explain the prompt emission with unmagnetized jets. However, it seems more physically likely that the dynamical timescales of GRBs, which are milliseconds, require the engine to work with some intermittency. It seems unlikely that a GRB duration of a few seconds or even more, a few orders of magnitudes longer than the dynamical timescales, will allow an engine that is working continuously. Therefore, this model, together with the fact that it naturally leads to the formation of internal shocks that can account for the variability, is motivated. And what we would like to see is, by carrying out set of 3D simulations of intermittent jets, whether this model can also explain all the observables. So we consider, due to numerical limitations, only time intervals of 0.1 second or more. And the minimum luminosity that we played with was between 0 to 20%. It can be more, it can be less. And we just wanted to see whether we can explain the light curves, the observed light curves. So let's start with hydrodynamic jets that are working intermittently. Here we found a very clear picture that rules out any hope for consistency with observations. And the picture was that every time that we turned off the jet, even if we just lowered the luminosity to 20%, what we found that happens is that there is very heavy baryon contamination that is filling the cavity that was formed by the jet, such that the next episode of the jet would encounter the stellar envelope as if nothing was launched before. So this cavity is closed very soon after, before the next episode is reaching the point where the baryon contamination took place. And therefore, we found this emerging picture of mini jets, no matter what the modulation timescale is. And that means that all the jet energy is going into accelerating this subrelativistic quasi-spherical outflow, rather than getting us something that is similar to a jet. We calculated the photosphere, and it turns out to be at least 10 to the 14 centimeters, very far from the star. At the same time, the subrelativistic outflow leads to coasting radius that is right after the star, much, much below the photosphere, and therefore the efficiency would be essentially zero. What about internal shocks, which is the initial motivation of this model? So internal shocks, they start promising with efficiency, average efficiency of a few tenths of percents, right? About 10 stellar radii. Our stars were on the order of 10 to the 11 centimeters. However, since at this point the medium is still optically thick, all the energy going from the internal shocks that is dissipated is going into accelerating the outflow rather than being radiated away. So by the time that this outflow is reaching a few times 10 to the 14 centimeters, the efficiency of the shock is a few percent at best. And therefore, these internal shocks can also be ruled out since they don't give us the high efficiency that we need for the prompt emission. So we can rule out this type of unmagnetized intermittent jets. And interestingly, we would like to see what happens if we introduce some magnetization to the intermittent jets, whether it can stabilize the jet just like we saw in the continuously launched jets. This is another type of instability. So this is not something that we can know without taking a full 3D simulation of mildly magnetized jets with intermittency. So here you see the isocontours of the jet when it has magnetization, when it doesn't have magnetization, and you can already see that the spine of the jet is more stable than in the case of a hydrodynamic jet. And the reason for that can be understood by looking at this picture. So here I show the reciprocal of the plasma beta parameter. So this is essentially the magnetic pressure divided by the thermal pressure. And this is the asymptotic Lorentz factor. So when the magnetic pressure is subdominant, you can see these blue parts, it corresponds to very low asymptotic Lorentz factor. When it's high, on the other hand, it corresponds to very high Lorentz factor. And this tells us that the toroidal fields that we put in the jet are sufficient to stabilize the jet against this baryon contamination that is coming during the episode at which the jet is not active, or at least it's only partially active. And this is enough to get us something that is very similar to the efficient photospheric emission that we found for the continuously launched unmagnetized jets, and therefore we find a high efficiency. At the same time, something that we see is that the variability timescale here is set by the central engine activity rather than the instabilities that we found in the case of continuously launched jets. And this is interesting because if this model is true, then we can learn about the central engine activity by the observations of the photospheric emission. If we see timescales of 10 milliseconds for the variability of the light curve, then it tells us that the central engine is also working on the same timescales. And this is a result that can be very interesting in understanding the physical mechanism that is powering the jet. Shorter variability leads to more stable jet, and this is why, even though we did not look into jets that are working on modulations shorter than 0.1 second, we can be confident that even if we would take simulations on shorter timescales, they would give us the same picture. And finally, and its main advantage over the hydrodynamic continuously launched jet is that here we can have a very efficient broadening of the spectrum by internal shocks, since the internal shocks in this model are found to be much stronger than in the case of the internal shocks that were induced by the instabilities inside the star. So we can mark this model as promising. In the 3 minutes that I have, I would like to discuss briefly preliminary results of the highly magnetized jet, which is something that we are still working on. So here, in order to have highly magnetized jets, we need to launch the jet self-consistently with Blandford-Znaick mechanism. So here I would like to show you a simulation of a full 3D GRMHD simulation of a collapsar model. This is the first collapsar model simulation in 3D GRMHD, with which the jet is breaking out from a star. So we have some angular momentum. We don't need to assume anything of the jet. We just assume some magnetic field profile. And we have the formation of an accretion disk. The accretion disk leads to the formation of the jet self-consistently. And the jet is formed from the disk, highly magnetized. So this is the upper panel is the density, the lower panel is the magnetization. And you can see that the jet is highly magnetized at the base. But after the collimation nozzle, the jet magnetization is dissipated to become weakly magnetized jet. Also, we can see that you cannot see it here, but in zoom in view, the disk is tilted, so the jet is also tilted. So you will be able to see it later. But anyway, the weakly magnetized jet after the collimation nozzle implies that our analysis for weakly magnetized jets is it can be applied also to this case. Here you can see that the disk was tilted, so the jet is launched with some angle of about 30 degrees. And therefore, everything that I told you about weakly magnetized jet might also hold for the case of highly magnetized jet, since this highly magnetized jet become weakly magnetized following the collimation nozzle. And this is a self-consistent simulation, and in this sense, it's also more promising than just putting the jet, injecting the jet by hand. So let me tell you just in my last slide a few things about what we would hope to achieve with this type of the first collapsar simulations in GRMHD. So one thing that we would like to see, and this is very relevant to prompt emission as well, what would be the observational effect of the tilt? So we see that the tilt is can even get to 60 degrees or so. So we have jets that are launched at all directions, and we would like to see if we can get any observational effect of the tilt, or it only takes place while the jet is still inside the star. What are the engine intermittency timescales? This is something that can be directly addressed with this type of simulations without inferring the intermittency just from observations of the prompt emission. Where the magnetic dissipation takes place, as I showed you, it looks like it's taking place at the collimation nozzle, and this of course has profound implications for the emission of the jet in the prompt emission if most of the magnetic energy is dissipated already deep inside the star. What type of progenitors support jet launching? We find that some progenitors support jet launching, some do not support jet launching, and interestingly, some support jet breakout and some do not support jet breakout. These are two different questions, and it seems like some progenitors have their own preference when it comes to jet launching and breakout. How does the jet reshape the supernova light curve? We find a very similar structure to what is found in supernova simulations, and seeing the jet and the supernova co-evolve together is something that has not been looked before. And finally, I would like to say that it's possible, just like with neutron star mergers, when we see the prompt emission followed by some kilonova emission, we know that in collapsars we also expect to have some heavy elements that are synthesized in the star, and whether these heavy elements can find their way outside the star is still an open question. But with these simulations, we can actually see whether the cocoon can carry these heavy elements outside the star to power some radioactive beta decay emission. So hopefully we will be able to address at least some of these questions, and I think that they are related to these big questions as it was put by Asaf in his talk. And stay tuned, and thank you very much for your attention.
Yeah, thank you very much for this very nice talk. So if you have questions, please go ahead. I see that Asaf is already very fast, so
yeah,
please start.
I have one comment and one question. So the comment, I really like your result about this recollimation shock. I actually think that we have indication for that in the data. So paper we published, I think was 2015. I think we actually saw evidence for that. That was the comment. The question I have, in the last part of your talk, you're talking about highly magnetized jet, and that they come from possibly the Blanford and Zweig mechanism. But the question is, you were talking about that in the framework of intermittent jets, right? Jets that are turning on and off. How can you get there in a highly magnetized jet? I couldn't get that.
So maybe you can rephrase the question. Okay, I'll try to answer, and let me know if I understood correctly. So what we have in the mildly magnetized and hydrodynamic case, we inject the jet by hand. So we basically set the modulations and we see how everything evolves. In this case, we don't set the modulations or the magnetization. We just put a star and some magnetic field configuration, and we let everything evolve self-similarly. So what we find is that the jet is launched self-consistently. It will be shown, yeah. So sorry. So you can see that the jet is episodic here. And this is because the power of the jet is coming from accretion onto the black hole. So the accretion is not continuous, is something that can be disrupted, for example, by the presence of the cocoon that can stall some of the infalling material. And therefore, the launching of the jet is found to be intermittent from the simulation itself. So in this sense, it's different. But the picture is the same picture that we put by hand, just this is something that the modulations are set by the accretion rate.
Okay, thank you.
Okay, Mukesh, please go ahead. And Tyler, I saw you also, I don't know if you have a question still, but okay, let's start with Mukesh.
Hi, what is the typical magnetic fields that you assume with the jet launching in the last case?
In which case?
In highly magnetized jets, what are the order of magnitude of the magnetic fields you assume with the jet launching?
Sorry, can you repeat the order of magnitude of?
Magnetic fields in highly magnetized jets at the launching of the jet.
So what we find, actually, this is one interesting result that we see, is that a jet would be launched as long as the Blandford-Znaiec, which depends on the magnetic field, the power of the Blandford-Znaiec can overcome the accretion power. So if the accretion power, which is the material that is falling onto the black hole, is larger than the Blandford-Znaiec power, the jet will never be launched. This is related to the question that I put as to what progenitors support jet launching. So we had to put magnetic fields that are leading to Blandford-Znaiec power that is larger than the accretion rate. So that depends, in turn, on the mass of the star and on the density profile of the star. So the steeper the density profile, the higher the density in the core of the star, and the larger the magnetic field that you need. And the shallower the density profile, the lower the magnetic field that you need. So it depends on the density profile of the star and the mass of the star. So for our canonical parameters, the initial magnetic field at the core of the star is about 10 to the 14 Gauss, something like this, but this again can vary depending on the progenitor parameters.
Okay, if this Wolfrite kind of star goes through this collapse, does it have that kind of magnetic fields? For example, if in observations it is seen to be having few thousands of Gauss.
So I refer to the magnetic field in the core. Observationally, we can only infer the magnetic field on the surface of the star, I assume. I'm not sure if this is the question that you're asking, and then it depends on what magnetic profile you're using.
Okay. Yeah.
Okay, so thank you for the questions. We have 1 more minute if there is more questions. Tyler, there is one from Hendrik. So please, Hendrik, go ahead.
Hello. If there was 1 minute for a question, maybe I can ask one quickly. I thought you need to worry about neutrinos and God knows what if you actually want to do this kind of self-consistent simulations from early stages onwards. Is there all sorts of extra physics that you didn't put in and can get away with, or that you did put in and did not tell us?
Okay, so thank you for the question. So as I mentioned, these are preliminary results. For some of the features that I showed, we have reason to think that including a neutrino scheme will not change the emerging picture. For others, we would like to implement some neutrino scheme. So this is something that we're working on, and hopefully soon enough, we will have M1 neutrino scheme that we will include in the simulations, and then we will be able to check consistency with the picture that I just showed you, which does not have any neutrino transport.
And this is all still with this Pluto code?
No, sorry.
I was about to say, that seems
yeah, I didn't mention. Pluto is a non-GR, is just special relativity, and this is called the Hammer.
Okay, so thank you, Or. Thank you for the very nice presentation. I think the next speaker is actually Gregory. Gregory, are you here?
Yes, I'm
Yes.
here. I'm giving a talk now. So just,
Okay, perfect. So it's your turn.
yes, yes. I'm giving a talk now. Just a second. Hello, everyone. Didn't mute yet. Okay, can you see my slide?
Yep.
Yes,
Okay.
yes.
Yes. The screen is better. Okay. So, what time is it now? Sorry, I'm a bit under pressure with organizational matters, you can probably notice. Anyway, let me start. I'll be talking about some topic which would seem to you probably not familiar, or for some of them already familiar, but not much familiar with respect to the topic we are discussing this session. So diffusion. Let me, the slide is changing. Okay, the outline of my talk is a little bit going back to Blackboard in the sense that when we started to look in this problem some 10 years ago, roughly, of course, people were understanding that this field is practically, the basics was laid down, so everybody understood what is photospheric emission and what is the basic model, what are the essential observational effects, but it turned out that actually there were kind of two competing models, and these competing models were completely unrelated, even if they were talking about the same matter essentially. And we understood that these two models were basically two extreme cases. Neither of these can actually take place in nature. So we were trying to develop a kind of consistent model which bridges these two extreme cases, and hence the model of finite relativistic wind came out as the dynamic model for the basis of the computation of the photospheric emission. So I'll remind very quickly what this implies, and also some outcome of this, in particular about the dynamics and geometry of the photosphere, which are essential to be understood before building up all the models with more complex physics. And then as a byproduct of this, it turned out that really physical mechanism which concerns photospheric emission in some relevant possibly cases was completely overlooked at that time. And I would like to pay attention to this mechanism because last year we made a kind of progress looking at the data, first of all, and trying to find some indications that this diffusive mechanism in the photosphere actually may take place in some, at least, cases of observed gamma ray burst, but this is not related to the previous topics which were just discussed in two talks. So not the prompt emission, but actually the thermal emission, which is inferred in the early afterglow of gamma ray burst. And then, of course, I will conclude. So let me say that, of course, the topic was nicely introduced by Asaf, who said that I actually would like to completely support the statement that apparently, at least from the physical point of view, the photospheric mechanism is a leading model in the sense that it is well motivated, well grounded, and of course is supported by the observations. But before going to some details about the specific details about the different modeling of this phenomenon, let's better maybe try to understand the foundations where we stand. This was the message we started to let's say launch 10 years ago, but still apparently there is some kind of confusion in the literature. So let me try to be more specific. There were the models by Goodman and Paczynski in '87. These are actually the two extreme cases in a sense, because Goodman considered a kind of impulsive explosion, and Paczynski considered a steady, completely steady physical situation. I'm sorry, just have to quit Skype for a moment, and then you will not see my pop-up screens. Okay, so they were considered really extreme situation because in the model of Goodman, that was certainly a transient event. In case of Paczynski, that was like eternal event he was considering, right? So actually, all the literature developed so far, only in the beginning, there was a kind of preference to Goodman models, Goodman treatment. Okay, instead later on, everybody switched to the Paczynski model of the steady wind. This is nicely reviewed in the literature, actually. And coming to the observational side, there was a very influential paper by Asaf with Peter Mejaros and Martin Rees in 2007, which actually related the physical parameters, hydrodynamic parameters of the flow, relativistic flow, to observations. And this is influential paper. It is used practically in all the recent inferences of physical parameters from observations. So we'll come to that. So I would like particularly to focus here in my talk on radiative diffusion in the photosphere, or actually below the photosphere. And therefore, my talk is not focused on the prompt spectra, on the prompt radiation, but instead in the early afterglow. So let me remind you the really standard part of the dynamic model. So there is assumption that there is a acceleration phase where the matter, baryonic matter, essentially with the radiation, is accelerated by the radiative pressure due to very high entropy, right? And sooner or later it becomes Costin. So there is a certain radius, a Costin radius, at which there is no more pressure efficient to accelerate further baryons. Therefore, from that radius on, the matter coasts. There is a relativistic flow of matter and radiation still coupled, possibly, but then the coupling of radiation occurs. So you will find at certain time or a certain place in space that the radiation no more scatters, no longer with matter, and this place is defined as the photospheric radius. And taking just matter conservation, you can find that the density in laboratory frame should scale as radius, inverse radius squared in this model. Well, we can distinguish two opposite cases when there is a kind of explosion. Therefore, this energy is released in the central engine on a short time scale compared to the size of the central engine, and this would of course give you a impulsive event, or if you expect that the energy release time scale is very long, and then you would expect quite a stable situation for a long time. Therefore, you can find the photospheric radius analytically from these assumptions, and you end up in basically three regimes: accelerating case, Costin phase, but actually Costin phase can be split in two parts, and one of them is what we call photon thick part, or photon thick regime, which is basically what people in the literature are calling steady wind, right? Instead, there is an opposite limit of the so-called photon thin case, where you can expect actually that photospheric emission would like completely different. And here is where diffusion actually plays the main role. You can argue that this regime is actually physically not much relevant, because this happens actually very far, way below the Costin radius, and therefore, because of the reasons mentioned already in the previous talks, it should not be relatively efficient. So let's not see any signal from this photosphere, but actually this argument is valid for the prompt radiation, certainly, but it is not valid for the early afterglow, where there is a strong decay in the observed flux. And you could actually see some additional components, and this is what I'd like to underline. So the physical difference between photon-thick and photon-thin regimes are that in the photon-thick case, the photons in that flow propagate on the flow which has the density changing, and therefore the photon actually kind of sees in front of it a long wind. Therefore, decoupling happens everywhere in the flow, decoupling of photons. Instead, the photon-thin case is a kind of thin shell, but it's not geometrically thin shell. It's a thin shell from the point of view, let's say, of the photon that propagates within the flow. So the photon will actually feel the presence of the boundaries in that case. So boundaries are not essential for photon-thick flow. Instead, they are very much essential for photon-thin one. And even this effect, the presence of the boundaries, actually, let's say, points you toward the importance of diffusion. Well, these two pictures just show you for the parameters, some parameters fixed. In particular, I guess here we get the initial radius at 10 to 8 centimeter. So it's a typical, more or less, radius which you infer from observations. For total energy of the flow ranging from 10 to 48 to 10 to 54 as function of the baryonic load or entropy in the flow, you can see different expectations for the flow. So for high entropy, you would expect that the flow becomes transparent, reach the photosphere at accelerating phase. For some intermediate case, it is in the coasting photon-thick, so kind of long wind, steady wind. Instead, for very large energy, quite small baryonic load, you expect large baryonic load, but small entropy, you would expect the relevance of the photon-thin regime. But this is certainly valid for short GRBs, because I guess if you consider 10 to 8 centimeters, so this would give you a fraction, a small fraction of a second for the duration of the burst. If you go to the luminosity, so the parameters would be not the energy baryonic load and the initial radius, but instead luminosity, baryonic load, and radius, you would see that this photon-thin regime basically disappears for relatively large eta. It will be still relevant for smaller eta, but this is not consistent, of course, with constraints on the Lorentz factor inferred from the per production, for example, from compactness argument. Okay, therefore, you're not expecting this photon-thin regime relevant for the prompt emission. Just to mention that photosphere in the static sources is different with respect to photosphere in accelerating flow. So our sun's photosphere, of course, everybody is familiar with. Betelgeuse, one of few stars optically resolved, so you can see actually its photosphere as well. So these are relatively steady object, apart from the fact that Betelgeuse was dimming for a while in a few months during this winter in particular, and this topic is discussed in some sessions in massive Gaussian. But these are snapshots to the right of accelerating flow and coasting flow, but in reality these are quite dynamical objects, the photosphere. Therefore, dynamics here is really essential. Well, Asaf was talking about some aspect related to the angular let's say dependence of the photosphere, radial dependence, but I would like also to point out the timing dependence of the photosphere. And this slide will show you some details related to this. So for photon-thick, so wind type of the photosphere, you would expect, first of all, type of concave surface. So it is well known that if velocity of expansion is relativistic, the shape of the photosphere would be concave. But with time, actually, it changes. So if we start close to the base of the flow, the shape is still convex, but then it becomes concave, and the probability of the let's say less scattering is distributed, and it peaks near the photosphere itself. Therefore, you still expect quite a broad distribution of radii, angles, temperatures, even if you have a steady wind or nearly steady winds case, right? But certainly for dynamical photosphere, it would be even more dramatic, this distribution. If you turn to the photon thin case, the shape of the photosphere is always convex, sorry. But what turns out is that the last scattering peaks, the probability of last scattering peaks not near the photospheric radius. And this is the first message which should be taken away from this presentation. What is relevant there is not the last scattering at the photospheric radius, but the diffusion process of the photons in the expanding flow. So let me remind you how you can actually assess this diffusion. So considering a diffusion time of photons in the expanding flow, therefore with changing density, you can compare it to the hydrodynamic expansion time of the flow, and making them equal, you can find where should this diffusion end. So basically taking typical photon which is propagating inside the flow with the random walk model, you expect that at that radius the photon will eventually reach the boundary of the flow and will just basically escape, right? So considering the two regimes, photon thick and photon thin, this is actually the latter where diffusion appears to be relevant. Therefore, the diffusion radius becomes smaller than the photospheric radius in the photon thin case. It means that the photons will be escaping from the flow before it gets transparent, therefore with high optical depth. This should not be really surprising, because we're talking about relatively large radii, and what is main message of my presentation here is that this diffusion of photons was completely neglected in the literature before we turn to this problem. Still, it is very well known actually, because talking about the stars, sun, little juice, and so on, but talking even about expanding flows in supernova, for example, you know very well that the peak of the optical emission in the supernova is fully due to diffusion of photons from the radiative decay and heating and the shock and so on. Therefore, diffusion should be really treated in this process of expanding flows. The point interesting here is that for relativistic flows, this is a kind of interesting process with its own physics behind. Therefore, let me just turn to the second part of my talk, okay, where we'll try to connect the physical points, the physical modeling of diffusion to the observations. And here we are going to use, of course, the well-known approach developed by Asaf previously for the case of relativistic wind. So first of all, let me remind you two points. The observed temperature in the outflow above the costing radius will be, of course, decreasing with the radius falling -2/3 power, right? So taking for initial temperature, which scales from the initial size of the flow down to the radius of emission, basically, okay, you will find the temperature much less than the initial one, clear. Then the duration of this emission would be given essentially by the radius of diffusion and inverse of the Lorentz factor squared, or the inverse baryonic load of entropy squared. This is already tells you something interesting, since we're talking about large diffusion radii, let's say order of magnitude 10 to 13 or even 10 to 14, and if we're taking relatively small values of the eta parameter, So the time of this emission, observed time of diffusion, can be relatively large. The second important point, which I mentioned already, radiative efficiency in this process is of course quite small because we are far away from the Costin radius. Therefore, the luminosity at the diffusion radius would be quite suppressed with respect to the luminosity of the jet. This is the point I'm talking about. And now let's turn to the approach developed by Asaf. So they introduced the parameter R, which is related to observables at the basically photosphere, right? So we can take all the surface where the emission happens, right? Black body emission, and diffusion is of course a black body emission process, right? So if we take the observed flux and we take the observed temperature, so we can find this R parameter, which can be related to the radius of emission, generally speaking, not necessarily photosphere, and the Lorentz factor of the flow. And there is a eta parameter of unity. And of course, immediately you can find from this observational parameter, knowing the redshift, you can find the so-called nozzle radius or initial radius of the flow. This is easy, but how can we obtain the Lorentz factor from these observations? So we need to rely on this relation between the luminosity and observed flux, which contains the fraction of the total luminosity to the let's say to the energy related in X and gamma rays in the Bromd phase. Keep in mind, this is the one different phase. So just taking that emission radius is the diffusion radius defined above, we obtain the Lorentz factor or the entropy as function of observed parameters, but there are two unknown, the fraction of luminosity here and the L, the thickness of the flow. This L parameter is something that is one of the basic parameters of this finite relativistic wind model, because you have, for example, luminosity, baryonic load, initial radius, and in addition, this thickness of the flow. So how can we obtain the thickness of the flow from observation? One might say, well, we have independent information of the duration of the photospheric emission. This is true, but at the same time, the duration actually is related to the radius of diffusion radius, but not to the thickness of the flow. So it's not a good idea to use the duration. Therefore, we don't have actually unique Lorentz factor for this diffusive regime, but we have a range, the full range of Lorentz factors from the minimal one, which can be obtained by equating the thickness of the flow to the initial radius. So assuming that the flow was launched and is not spreading, this would be the minimum duration, minimum thickness of the flow, and it will actually give you the minimum Lorentz factor, the lower limit, which is consistent with the regime. Instead, if we go to the largest possible thickness of the flow, which will be related to the diffusion radius itself, we go back to the standard formula in Asaf's work of 2007. Therefore, you get the range between the minimum and the maximum here, consistent with the diffusion of photons below the photosphere. To look at this in observations, we took the paper of 2018 of Valan et al., which contains a number of bursts with known redshift, known fluxes, and known luminosities, and therefore this was a basis for this work. So if we take all these, average the observational, average the observed characteristics from the tables provided in that paper, we can consider several sources, right? Assuming averaged averaged observed parameters for them, and analyze each of them, and applying these equations, looking at the possible variance factors, which we can recover. So there are actually two typical cases, and all these sources will be actually distributed between these two kind of typical cases. So one typical case is the source 090618 with the initial radius of 10 to 9 centimeter, quite large, and the Lorentz factor in this case range from 3 up to 40. So 3 is the lower Lorentz factor obtained from that formula. Instead, 40 is the one given by the formula for the wind. And taking that, okay, assuming that the thickness is equal to initial size, one obtains for Y parameter 5.7. And the duration of the thermal emission in this case would be about 6 Y seconds. I remind you that the offset of the beginning of the thermal component here is not determined by any parameters. So this is early afterglow. This is not the prompt phase. So in principle, you can have any offset between the initial emission obtained in the prompt phase and the early afterglow. And of course, this is consistent with the observed temperature of the order of 1 keV. So this is quite a large Lorentz factor. You can see still smaller, much smaller than the one in the prompt phase, but still quite large. Another case, typical case, is 11, represented here by 111225A. And this is also, by the way, similar to famous 06 or 218. Here we're talking about initial radius, quite similar, about 810 to 9, larger than the one in the previous case. And the Lorentz factor range is between basically 1, so almost non-relativistic, up to 6, right? And the duration in this case would be up to 100 seconds in the NMR, right? And the typical temperature in this case, average temperature is 0.18 kiloelectron volt. So these two cases, you can see, have different Lorentz factor, ultra-relativistic in the first case and possibly mid-relativistic in the second case. So they call for different physical interpretation of the origin. So if we talk about the first one, it's very likely that this is a relativistic flow, possibly a jet or another different type of event. If we talk about the second case, this is possibly consistent with the cocoon, jet cocoon, which emerges when the jet break out from the progenitor star. What did I want to say here? Yes, so considering that we have in this model of the finite flow, basically two different regimes, we can interpret a photospheric emission with large Lorentz factor as the one which is explained by the traditional photospheric emission of the photon peak emission, or basically steady wind kind of emission. Instead, for relatively small Lorentz factor inferred from the observation, this could indicate a different physical origin of the emission, namely diffusive one. Of course, there has been a large discussion about possible physical origin of the thermal emission in the early afterglow, and two competing proposals were the cocoon itself and shock breakout in the surface of the star. Regarding the shock breakout, the luminosity seems to be required quite large compared to what is possible to obtain from on the physical grounds based on the parameters of the progenitor and so on. if we are talking about the cocoon, my basic message here is that the traditional photospheric model, which considers emission from the photosphere itself, fails in this case simply because small Lorentz factor tell you that emission should originate below the photosphere, even if this is still a photospheric emission, but this has nothing to do with the photosphere itself. This is emission by the normal diffusion of photons, because photons simply reach the boundaries of the flow faster than they reach the photosphere, and therefore they will be emitted and received by this observer. Actually, in my abstract, I promised also to say a few words about the diffusion. Sorry, not diffusion, by dissipation. But I would like just to say a few comments. There is nothing to show you from the point of view of the calculations, but just a few comments. When we are talking about dissipation, you are talking about taking basically some part of the kinetic energy, converting it somehow at some place into radiation. And taking part of the kinetic energy implies deceleration of the flow. So looking at this diagram, you can see immediately. So if you start with coasting photon thick flow, therefore kind of steady wind, you can easily, by changing the eta parameter, decelerating it, you will actually end up in the coasting photon thin case. Therefore, diffusion may become relevant, even if initially it was not relevant there. And since you are taking additional energy, converting it in radiation, the problem of efficiency, which I mentioned before, would not possibly apply. The second message is related with the geometry of the flow. When we are talking about photon thick emission, you can see the shape of the photosphere is concave, but actually the size of this, I mean, if you are looking from a different angle, this is very much angle dependent picture. This is with respect to the line of sight here. If you are looking from a different angle, say 90 degrees, the photosphere will be much farther. And the physical effect here is that the photosphere is relatively compressed along the line of sight, and the compression factor is gamma squared. So what could happen when you have dissipation in this kind of flow is that since you are reducing Lorentz factor, so you can actually make the photosphere farther away. If you're making the photosphere changing the photospheric radius, it becomes farther away, which is rather natural because you are keeping the number of electrons scattering in the flow, but you are decelerating the flow, so the boundary will be, let's say, kind of farther in this case. What you expect is that the efficiency of photospheric emission will be reduced. Just looking at this problem plainly like this. But maybe I think some more careful examination of the dissipation is important here, considering this effect of the presence of two qualitative regimes in the photosphere, maybe the traditional photospheric emission and the diffusion below the photosphere. So I think I end up here. I don't know if I was really on time or not, and I'm ready to take your question. These are the references of all the works I mentioned, and the last one, number 8, is the paper on which my talk was based. Thank you very much.
Okay, thank you, Gary, for the very interesting talk. So time for questions.
I'm not running away, just close the window when you have some disturbance, please.
I just have a confusion.
Yeah, go ahead, Mukesh, go ahead.
Yeah. In the penultimate slide of your talk, the previous slide and the last one, it appeared that the lower limit of the Lorentz factors, one of the GRBs was less than 1. So you may have already answered. I'm having some sound issues here.
I'm sorry, I could not get anything. Let me try. Maybe this way would be better. Can you please repeat the question?
Yeah, in the last but one slide, the previous slide where you were showing some case studies, it appeared that the lower limit of the Lorentz factor in one of the GRBs. No.
Yes. Okay. Now was there? Just a second. Yes, here.
Yeah, it appeared that in 090618, the lower limit is coming out to be less than 1 of Lorentz factor, or I'm getting it all wrong.
You mean here?
Yeah, when you put this y equal to 5.7.
Well, good question. Thank you. Actually, of course, we're talking about analytic models, and the basic assumption in this analytic model is that we are in the ultra-relativistic regime. Therefore, Lorentz factor should be certainly larger than 1, much larger than 1. Here, we're squeezing quite the available range. Therefore, Lorentz factor, let's say, should be certainly still quite relativistic. So let's say 3 at least. 1 is just put here by there's no formula. This formula simply tells you that Lorentz factor should be as low as possible, but it cannot be lower than 1.
Okay.
I think it was actually for 090618 by just putting y inside 3 times y.
Possibly. Yeah. Well,
yeah.
Go ahead. Sorry.
We're talking about order of magnitude, of course, but certainly we understand that Lorentz factor in this model cannot be less than 3, let's say, for sure.
Okay, is there other questions? No other questions? So if there is no other questions, then we will start the last talk of the day, right? Okay, so please, Tyler, it's you.
Yeah, thank you. Let me go ahead and try sharing my screen. Let me know if you're all not able to see my slides. All right, is everyone able to see that?
Yes, absolutely.
Okay, great. Well, thank you all very much for having me here to speak about my work that I do at Oregon State University with Davide Lazzati. I'll be talking about our Monte Carlo simulations of photospheric emission in gamma ray bursts on topic with this session, of course. Here's an outline of what I'll be talking about today. I'll give a brief introduction on the gamma ray burst models, which we all know. I'll talk a little bit about some simulations that explore photospheric emission. I'll talk about our ICRANet code, what we use to produce our results. I'll also talk a little bit about how we construct mock observations from the ICRANet code, in particular using this process ICRANet package. Then I'll go into some results that we've acquired relating our mock observables to the simulated jet structure and some predictions that we've acquired under the photospheric model. And then I will conclude with a summary. So a brief introduction for those of you that may have forgotten a bit about gamma ray burst prompt emission models. There are kind of 2 areas of kind of describing the prompt emission. That is the photospheric model, and then models that kind of fall under synchrotron emission. Here on the left, I'm showing you a figure from Garrick et al., where they show the gamma ray burst jet, and you have this thermal emission that's produced deep in the jet, and as the jet becomes optically thin to that radiation, it becomes advected out, and that's what we detect as gamma rays. Now in this model, the photospheric model, we have a few tunable parameters: the structure of the jet, dissipation processes, as we've heard in a few talks, and of course, the location of the observer with respect to the jet axis. Now, on the synchrotron emission side of things, I have here a figure from Zhang et al.'s paper showing their ICMART model. There's a few different tunable parameters. There's the structure of the magnetic field, there's time scale over which electrons cool, and once again, where the observer is located with respect to the jet axis. And all of these tunable parameters in each of these categories of models have allowed each set of models to be able to replicate a number of gamma ray observations. What we need for the purpose of model selection is to be able to further kind of define these models, extend their range of predictiveness to other energy bands. And that is kind of what I'm showing here in this slide, where there have been a number of optical prompt emission detections, here shown in that table to the right. And typically when these optical prompt emission detections are kind of discovered, then they're correlated with the gamma ray prompt emission. That's kind of when we say that this optical emission that is detected is actually related to prompt emission. An additional criteria for that is that the optical spectral energy density is typically accounted for when we fit the gamma ray spectrum. And with a lot of these detections that you see here on the table on the right, these optical detections have been attributed to synchrotron emission, particularly from fast cooling electrons. Something interesting that has happened recently is that Ogana-san et al., in kind of analyzing some of these optical prompt emission, they fit their spectra with a synchrotron model, and they try and determine something about the emission region of these gamma ray burst jets under the synchrotron model. And they actually find properties, be it electron number, Lorentz factor, things like that, properties that are in tension with a number of other analyses of gamma ray burst prompt emission. So this is kind of an area where we can use the photospheric model to potentially explain some of these optical prompt emission detections. One thing that I would like to point out before I move forward is that here in red, I've highlighted one detection where we do have an optical prompt emission that has been coincided with also a optical polarization measurement of that same optical prompt emission there. But the main idea of this talk is that we need to increase the predictive power of the photospheric model. We really need to step up what we're able to say the photospheric model provides for us across the electromagnetic spectrum. So as many of you know, the study of gamma ray bursts, I'll be focusing mostly on long gamma ray bursts, has been broken up into kind of two main areas: those who study the jet propagation side of things, and those who focus mainly on the radiation transfer side of things. Now, looking at the jet propagation side, it's relatively straightforward to run your hydrodynamic simulation where you inject some sort of energy into a star. Here you could see that jet developing inside of the star in the left-hand panel. On the right-hand panel, you see that jet propagating out of the star and breaking out of the surface. And simulations like this allow us to really understand collimation shocks, such as what Ore showed us, and really start to understand how the jet is structured. It doesn't allow us to really look at the radiation signature, however. In order to get some idea as to what the radiation is doing, a very typical assumption is that the radiation and the matter in the jet are perfectly coupled up until some radius, the photospheric radius, at which that coupling immediately drops to zero. So you get this unphysical treatment of the radiation, but it allows you to go from your hydrodynamic simulation to something that you can compare to observations, which is of course what we always want to do. Now on the radiation transfer side of things, the situation is the opposite. We're able to conduct self-consistent radiation transfer calculations, but they're done in very simple analytic outflows. For example, this one profile that Asaf had showed us earlier, where we have this Lorentz factor profile giving us an inner-outer type of jet with an envelope. Once again, these types of assumptions about the jet on the radiation transfer side of things allow us to make comparisons to observations. Now, in order to have a deeper understanding as to what the photospheric emission can tell us about gamma ray burst jets, the structure of jets, so on and so forth, we need to get rid of these two assumptions. What we need to do is we need to conduct self-consistent radiation transfer calculations using the background of a realistic jet profile. And that's exactly what we do using our MC-RAT codes and the process MC-RAT code as well. Then once we have conducted our mock observation, which I'll show you in a few slides, we can make comparisons to observations on a more equal basis. So what does MC-RAT do? Well, MC-RAT is our Monte Carlo radiation transfer code. It's open source, available for anyone to use on any of their hydro codes. It takes hydro simulations. Here I'm showing you our variable simulation here on the left, 40 spike down. And on the right-hand side, I'm showing you the pseudo-color density profile of our constant 16 Ti jet profile. You can immediately tell that here in the variable simulation, we have these striations in the jet. On the constant side, things look fairly homogeneous. What MC-RAT is doing is it takes these hydrodynamic simulations and it places these photons into the outflow. and it individually Compton scatters and propagates those photons using the full Klein-Ostrina cross-section, including polarization. And as I'll show you a little bit later on, we're able to include cyclosynchrotron radiation into the code as well, which allows us to simulate emission from optical all the way to gamma ray energies. Now, once these simulations are done, we can collect the photons and conduct our own mock observation of this simulated gamma ray burst jet. And that's what we use our process ICRANet code for, which is also open source and available here on GitHub. We collect our photons for a given observer located at a viewing angle off of the jet axis, theta v. We identify which photons arrive at our observer at what time. We identify the weight of each photon, and the weight is simply a measure of how many physical photons each Monte Carlo packet represents. And altogether, we're able to construct light curves, time-resolved spectra, polarization degrees and angles, and get a whole lot of information that we can compare to observations. So I'll be giving you a few, actually a little taste of what we're able to do here, and then I'll jump a bit more into the optical portion of things, some of the newest results that we've acquired. One thing that we're able to do with ICRANet is we're able to look at effectively how high latitude photons contribute to the spectra that we observe, quote unquote, observe in ICRANet. So what I'm showing you here is for an observer that's located 1 degree off the jet axis. They are observing photons that are within this plus or minus 1 degree cone here. And if they do that, then this observer detects the spectrum shown in red, which has the band parameters shown by that dashed line. If, however, we look at all of the photons in the outflow, all of the photons that we've simulated in ICRANet, then what we end up getting is the spectrum shown by these blue points here, which is more of your typical gamma ray burst spectrum. Of course, you have this negative power law energy slope, or excuse me, power law photon slope at low energies, and you have your power law slope here at high energies as well. That's very typical. So we're able to go in and understand how these high latitude photons contribute to the spectra. Additionally, we can go in and we can take our mock observations and compare them to things like the Golinetsky relationship. Here I'm showing you the Golinetsky relationship as this gray line, and its 2 sigma dispersion as this dashed dotted line. And I've taken our 40 spike down simulations for a variety of different observers, and I've plotted each of their time interval luminosities and their time interval spectral peak energy. And you can see that majority of the points fall very nicely within the Golinetsky relationship. So we're very confident that photospheric emission is able to reproduce the Golinetsky relationship. Additionally, we can go to the Yonotoko relation, and we recover results that are very, very similar to what Hirotaka found, where here, this gray line is the Yonotoko relationship, and we've plotted some observed gamma ray bursts as well here as circle markers. Our 16 TI and 40 spike down simulations, constant and variable simulations that is, for a variety of different observer viewing angles, fall very nicely along the slope and the normalization of the Yonotoko relationship. Once again, reaffirming Hirotaka's finding that the observer viewing angle is able to recover this relationship. So with some of these results, I do want to switch gears, as I mentioned, to looking at the optical portion that we're able to now look at. What we're going to do is we're going to relate some of these observables, these mock observables, to the structure of the gamma ray burst jet. Here on the left-hand side, I have 3 different panels. In this top panel, I'm going to be showing you the time-resolved spectra of the photons that I'll be showing you. I have 2 highlighted regions here, one for the Swift UVOT white filter, optical filter. Here I have kind of the Fermi band where typically the band spectrum is fit, Comptonized spectrum is fit. In these bottom 2 panels here, I've got our bolometric light curves, so considering all energies of photons. And I've also got our optical light curve, which is constructed within the Swift UVOT white filter. What we're going to do is we're going to step through our light curve. Here we have these 2 black dashed lines that kind of show the time intervals. We also have the same time intervals being shown on this right-hand panel where we're plotting the pseudo-color density of our gamma ray burst jet that we've simulated. This is for an observer that is 1 degree off the jet axis, and I'm plotting their direct line of sight from where they're located down to the central engine. And additionally, you're going to see blue and red markers, blue representing your bolometric photons, red representing your optical photons. And they're going to have different sizes based upon their weights, based upon how much they contribute to the spectrum, to the light curve. So let me go ahead. I'm going to start this animation here. And we're stepping through the light curve. Here on the left, we're stepping through the structure of the gamma ray burst jet. And here you see some of these photons that are appearing in the jet and how they affect the spectrum, or spectrum in the top left panel, and the appearance of the light curve here in the left bottom 2 panels. What you might be able to see immediately is that there's a whole lot of red out here towards the outer edge of the gamma ray burst jet. This is pretty much the cocoon out here. And these red markers represent the optical photons. So being able to detect optical prompt emission under the photospheric model, that is able to provide information about this higher density cocoon region of the gamma ray burst jet. Now, a lot of the bolometric photons, primarily actually the gamma ray photons, are coming from directly along the observer's line of sight, which is exactly what you expect. These are the photons being Doppler shifted or Lorentz boosted into higher energies that the observer sees. So what we're able to do here is we're able to actually take these mock observables and relate them to the structure of the gamma ray burst jet, which is an extremely powerful feature of the ICRANet code. One thing that we can do is we can start to look at how the optical peak of the light curve decays as a function of observer viewing angle. And that's exactly what I'm showing you here. On the x-axis, I'm plotting the observer viewing angle. On the y-axis, I'm showing you the normalized maximum of the light curve, both for the bolometric and the optical light curves. And one thing that you can immediately notice is that in the case of the 16 Ti simulation, the bolometric light curve decreases very rapidly at high observer viewing angles. The optical light curve peak, however, stays relatively shallow, has a relatively shallow decay, same with the 40 spike down simulation. So you can kind of infer that at some point at large theta V, your gamma ray light curve is extremely dim and our gamma ray detectors won't be triggering on a given event. However, our optical light curve is still relatively bright. And so it's possible that we would be able to detect some sort of optical signal there. Another thing that we can do is we can look at how well the optical and bolometric light curves are correlated, both for the 16 Ti and the 40 spike down simulation. Here, looking at the 40 spike down simulation, I'm showing you here as the dashed red line, and it's 90% confidence interval for each of these values is shown by the highlighted region here. And we can see that there's very, very mild positive correlation between the optical and bolometric for our variable 40 spike down simulation. Things change drastically when we look at our constant simulation, the 16 Ti simulation, where at less than about 5 degrees, we have very strong positive correlation between the optical and bolometric light curves. Then that switches to be a negative correlation between the two. And then it kind of goes to be a mildly positive type of correlation. So as I mentioned in the introduction, a lot of the optical prompt emissions have been found to be well correlated with their gamma ray light curve counterparts. And that's kind of indicative based upon some of our results here of observing that gamma ray burst on axis relatively. So that's a pretty interesting thing that any type of positive correlation, at least under the constant simulation jet, that kind of shows that we're viewing it on axis. A little bit of a negative correlation, then things get a little bit more interesting there in that aspect. One other thing that I'd like to touch on is looking at the potential for optical precursors. And what we find is that we do expect there to be some sort of optical precursor by up to tens of seconds, especially in the case of a steady jet. So what we've done here is we've constructed this tau parameter where tau greater than 0 shows that the optical prompt peak occurs later in time than the bolometric peak. Tau less than 0 shows us that the optical prompt peak occurs earlier in time than the bolometric peak. And immediately you can see that our 40 spike down simulation here shown in red, for the most part, has positive tau, meaning that for a variable jet under the photospheric model for this simulation, we would expect the optical prompt peak to occur later in time than the bolometric peak. For the 16 Ti simulation, where we have a constant jet, we could see that at large theta V, we expect there to be optical prompt emission occurring earlier in time than the bolometric emission. And the bolometric is typically dominated by the gamma ray emission. So we expect there to be some sort of optical detection and then a rise in the gamma ray detection. That changes though when you start getting very, very close to the jet axis. Here, we would expect there to be an initial bright gamma ray burst that we would typically see. And then after that, we would expect there to be some sort of optical prompt emission coming a little bit later on, which is interesting. So I've shown you a lot of things. Here is my summary. We've created this open source MCRAT code, which takes a number of radiation processes into account, and it is open source, available to be used by anyone on their hydro codes, specifically Pluto and Flash simulations. And being able to conduct these global radiative transfer simulations really improve the predictive power of the photospheric model, which is something that can really help us test this model and push it to the next level. I've shown you that we can connect the mock observables from MCRAT to the actual structure of the simulated gamma ray burst jet. In particular, when looking in the optical region, as we are now able to simulate, our simulations only provide lower limits. In fact, when we construct an observed magnitude for one of our largest optical luminosities, assuming a redshift of 1 for that gamma ray burst, we still get something that's a factor of a few dimmer than some of the dim detections made in that initial table that I showed you. We do, however, expect there to be optical prompt precursors, especially for off-axis viewers by up to a few tens of seconds, especially in the case of a constant gamma ray burst jet. Additionally, optical and bolometric light curves that are well correlated with one another are indicative of observing the gamma ray burst on axis. And in future analyses, we will be looking at polarization in the optical prompt region and comparing that to the currently one optical prompt polarization detection by Troy et al. And this will additionally push the predictive power of the photospheric model and really, really test what we think we know about it. With that, I thank you very much for your time, and I have a number of papers up here for you to reference, and I'd be happy to answer any questions that you have at all.
Okay, thank you very much, Tyra, for your very, very nice presentation. So I see that there are already 2 questions. Yeah. I think, Michael, you put your hand before, so please go ahead.
Hi, yeah, thank you a lot for this talk. And I really find it, I mean, this is the good direction that you have to make your models open so that observers can test it. So I have kind of 2 questions. When you're showing, I guess, the fits to the band function with your data there, you're not folding through any instrument response, correct? It's just
I am. Absolutely, and that's something that I'm very interested in, actually. I will be joining the SWIFT group in the fall, and I hope to be able to really fold in instrument response functions and start to play around a little bit with some of the data pipelines for doing fittings and things like that.
Yeah, I have some open source code as well that will already do that for a bunch of instruments for you. And also, I was curious, yeah, I can email you a link afterwards.
Absolutely.
But yeah. I was also curious then, so you could basically, I realize your model is time dependent as well, but you could basically create a table model from your results, and then we could, when we want to do fitting to the actual data, take that table model and fold it through the response, etc. So, I mean, is your code the code that's available already? Would I be able to do that myself? Would I need to contact you to figure out how to run it? What's the best way?
Yeah, so the code that is available, there is documentation that I've written up and everything for that. So ideally, it is, you should be able to read the documentation and be able to run it yourself and do all of that. In practice, that may or may not be the case. So you're more than welcome to email me, and I'd be happy to answer any technical questions and help you with that for sure.
Cool. Thank you. And thanks for making your code open source.
Yeah, of course. I think that's definitely the way to go.
Okay. Thank you for the answer. Next question, Asaf.
Yeah, well, thank you for a very nice talk. I have a basically technical question about the code. Is it a fast light code? Namely, you're assuming that the photons are just moving through the plasma, or is it or maybe another way of phrasing it is to what optical depths can it handle? How many scatterings can it handle?
Yeah, so it can handle a lot of scatterings. The way that we start our simulations is that we start off with the black body spectrum where the optical depth of the jet is at least 10 to the 3, 10 to the 4-ish. And we just allow the photons to go at that point. And they undergo, on average, that many scatterings before the end of the simulation. And so it's the technical way that the code works is that we inject these photons in the co-moving frame. We're constantly switching frames, which makes it a little bit confusing. We inject the photons in the co-moving frame, so they're co-moving with the fluid, and we actually calculate their energies in the lab frame, which is how we're able to construct our mock observables at the very end.
But
hopefully does that answer your question at all?
Well, I guess again, since the photons evolve, right, while the dynamics evolve, right, while the gas evolves as well. So when you have like some interaction, then the properties of the gas are different than the properties the gas had while the photons were, let's say, emitted, or one last before scattering. So I guess my question is, how are you taking this into account, like evolving simultaneously the photon field with the gas?
Yeah, so we're not doing radiation hydro. This is a post-processing type of analysis where you run your hydro simulation. And when you do your hydro simulation, you have a certain time resolution, but from one frame to another, be it 0.1 seconds, for example. And you say in frame number 1, time 10 seconds, let's say, this is what the jet looks like. And you're going to scatter your photons until the time in the simulation corresponds to frame number 2, so 10.1 seconds. And then you reload the simulation frame, and you say, this is what the jet now looks like, and then you scatter. So it's a little bit of a play between having the proper time resolution in your hydrodynamic simulation such that you're not just shocking the photons and giving them an unphysical amount of energy. It has to be a gradual change, of course, to make sure that you're not introducing any sort of errors that I think that you're alluding to.
No, okay, thank you very much.
Yeah.
Okay, we have one more question. Or please.
Thank you for the nice talk. I just wanted to ask about if you have any intention of applying this code to 3D structures, which are very different than 2D ones. I'm not sure how complicated it is.
Yeah, that's definitely something that I want to do. Extend the code's capabilities to run on potentially, some of the 3D simulations that you have, especially the 3D MHD simulations that you have. I think that would be extremely interesting to see, the actual radiative transfer differences from just hydro to MHD and what that can mean for actual observables.
And is it possible to use the code for 3D data, or it's not?
As it stands right now, it's not implemented, but it's definitely something I'm interested in, and we could talk more about that. And yeah, it shouldn't take long to implement. The code is pretty. The way it's designed is it should be quick to implement.
Okay, great, thank you.
Yeah.
So we have one more question, Hendrik.
Yeah, sorry if Asaf already sort of touched on the question. Yours is a post-processing code, right? So your bottleneck is not going to be your simulation time step, but your data dump time step, presumably.
Yeah.
And I guess if that is not sufficiently well sampled, you just sacrifice the variability timescale of your prediction.
Yeah.
Can you further comment on that? For example, when Aura wants to have a bazillion 3D data dumps for his, that may be a tall order, actually.
Yeah, that's a really good point. And I think that that's something that we need to do some more testing on, and maybe implement some interpolation and things like that into the code to make it more efficient, such that you don't have to have terabytes and terabytes worth of hydro data that you have to save.
All right.
And simply a question: why can't you do it on the fly? This is basically just adding one loop to your MHD code in the middle.
Yeah, you could. So Pluto, for example, has radiation hydro currently. They do it, I believe, in the gray approximation, but and that will help do things such as get the structure of shocks correctly. But you obviously won't get the full spectrum. And I think that that's a current limit of radiation hydro right now.
Okay, thanks. Is there other questions? So I see that there are no more questions. So now we will have small discussions. Is that okay with you? So Gregory will take over from here. So please go ahead.
Yeah.
Okay. Can you hear me?
Yes, yes.
Okay, so if you like, you can actually switch on your webcams just to see some live discussion, since we basically ended with talks. Well, this was not actually intention to have discussion in the middle of the session, because tomorrow we'll have some additional talks and probably would be better. But anyway, it happened this way. So just trying to summarize what we hear today and what is the main message of these talks, and also more or less what we can read in the literature. I think it would be fair to say that first of all, observations are really driving this field. I mean, gamma ray burst, prompt emission, and afterglow emission. This is safe, and this is very good actually to have this observation in the drilling field, because after all this news of the very high energy photons detected by MAGIC, for example, and has recently, right, and also different news also with the source 17 or 817, which will be discussed extensively during the meeting, which does not fit more or less what people were expecting, and so on. This is generally speaking about gamma ray burst, but particularly speaking about the photospheric models, I think we are also, I don't know if you share my vision, but I think we are still in kind of an infancy for this field, because even if models becoming more complex, but I mean, we can still see that a lot of physical effects are not yet accounted for. I was trying to give an example for that, but we can see also during the discussion that this is so. And the physics is quite rich, unlike what people were thinking in the beginning. These were the first ideas were put forward about the black body emission, photosphere, and so on. We can see various really important directions to be understood. Polarization, just to mention a few, polarization and what all this, I mean, this is not yet even observed, let's say, with good quality, but this is the whole area to be explored. Dissipation, clearly we are in terra incognita, so we don't know yet really even a physical mechanism. I mean, there are many, we can list them, but we are not certain about any of them actually. And well, diffusion again, to tell you my favorite topic, right? So we need, of course, certainly more data on this and more complex models. Any problems that you see, of course, I would like to hear all of you, not just me speaking here, but problems that I particularly see is that probably we are a little bit disconnected, as is quite often in this field. Everybody's pushing his own model. We can hear this many times, but to say more specific, probably we are going in too many details with each model, paying attention to too fine structure without looking on the overall picture. I think this was also a point mentioned by Asaf in his talk. There are many unresolved issues yet, in particular the origin of the jet, the mechanism of dissipation, possible effect of the environment of the central engine. So this is related also to progenitor model and so on and so forth. But anyway, yes, and one more specifically interesting point I want to say that this in the talk we just heard, the connection between variability of the source, right? Variability in observed variability time. Is this related to the structure of the jet, or is this reflecting somewhat central engine activity? So can we, after all, the basic physical question would be, can we, from the observation, infer anything about the central engine, or we are just looking at the hydrodynamic structure of the jet? So this would be one of the main questions, I think, which are still to be answered. Well, what do you think, Asaf? Maybe we can start with you. Can you share your idea?
Not sure I have much more to add from what you said right now and what I said. It's I mean, basically, I agree with most of what you say, which is kind of boring for a discussion. I agree that you see, from my point of view, and I've been in this field for long enough, right? It looks like things go with trends. You know, sometimes there is something which is trendy, and everybody seems to be doing that. But the fun part is what I mean. The criticism here is that people do something trendy without really solving previous problems. I mean, so for example, plateau is a classical example. I mean, people were working on that for a long time. It was a very hot topic for a while, and then nobody really solved it, and then people kind of left over to the next interesting point. You know, actually, this is sort of a promotion because we'll give a talk about plateaus, but this will be in another session.
Right.
Yeah, I mean, I agree. It's driven by observation, which is very good. There are observations, which is very good. It's not a dead field, on the contrary. It's a living field with new results. Are we there? No, we're not there yet. Will we be there? Likely, yes. I mean, you see that the last trend is that a lot of people are doing now numerical simulations, which become more and more advanced. People were doing numerical simulations also 20 years ago, but not 3D, not with full GR, not with full radiation. So obviously, we have stronger and stronger tools who will nail it eventually, like the yes. Yeah, I'm not sure that I'm saying much useful things at the moment. Maybe you want to want to ask the other guys around here.
Sure. Anybody likes to join the discussion, please. I mean, we are just sharing ideas. It's beneficial for everyone.
I think one of the problems that we actually have is that you have been saying for now 3 hours that the field is driven by data, and that's somehow good. but somehow we also would like to go the other way around, right? So basically make the bridge between the theory and the data, and not the bridge between the data and the theory. And so I think when it comes to photospheric emission, this is a very difficult business because the possibilities are, there are so many possibilities. There are so many effects that needs to be taken into account so that we can explain the spectrum. So it happens quite often when I'm actually speaking with people doing data analysis that I'm always ending up saying something like, okay, well, this model might not be able to explain this, but you know, there are all those effects that are not taken into account. And then maybe you can explain broader slopes, low energy slopes, I mean. And I think somehow we are lacking predictability. And actually in the presentation today of Tyler, and I actually really like it because I have the impression that this is a direct first step between the simulations and then the data, right? You are actually able to produce a spectrum. You are actually able to produce observables that will, in principle, that you can in principle test. But then that also carries its weight of open questions, like for instance, what is the sensitivity to the initial conditions that you're putting in your simulations? Do the spectra depends, I don't know, on the content on the jet and all those kind of things. And how much can you then say with the data when you're actually comparing your result? And so I think, yes, now the field is driven by data. It has been a lot. So we are able to get the right peak energy, about the right peak energy, about the right luminosity. But now the question, I think, from the theory perspective is, can we actually produce something that can be used so that we can actually go forward and test that directly with the data?
Actually, I want to comment on that, if you allow me. You know, there was a meeting in Nanjing, something like 2 or 3 years ago, just before the corona. And I actually heard Tzvi Piran, of all people, was one of the people working the longest on this field. And it was, he gave a comment which sounds really strange to me. He says that he thinks that, you know, since every GRB is different, then we might simply not be able to come up with a model that that captures all of them. But I actually think the opposite. I actually think that yes, there is a lot of noise, but you know, everywhere in life you have to reduce the noise and get the signal. And I actually think that we did manage and we will manage to get the signal. Now, I do agree with your criticism. No, a lot of people here are doing numerical simulations. And I'm looking at that with cautious. I mean, I agree that they can give you some things that you cannot get analytically, but I agree that you're very sensitive to the initial conditions and to the things that you actually put by hand. Sometimes you don't even know that you put it by hand, but you actually do. And so you have to take them with a great cautious. Still, I think that we are able to, you know, we have to remove a lot of noise and a lot of scatter. But after we do that, I think we do see an emerging picture. So I'm not that pessimistic as what it seems that we presented.
It was not a matter of being pessimistic. It was a matter of being able to progress, right? Can we differentiate one progenitor from the other one? Can we differentiate a physical scenario from the other one? That was more.
I actually think we can. I think we can. We have to remove noise, but I think it's definitely possible. Well, we're doing that right now. No?
Can I ask a more general question on that same note? More from an observational perspective, not mine per se, are there any observations that we are hoping to see in the coming years that will make a big difference here? For example, including multi-messenger stuff like neutrinos, or any upcoming missions that will hopefully find a sweet spot somewhere in the spectral range that may make difference for the photospheric emission models.
Okay, for me, the most promising thing which is already there is polarization. I think there are now, you know, there were several attempts which were failed. And I think now there are ongoing satellites dedicated or have very strong polarization capabilities, like the Indian mission. And I think that's the most promising in terms of statistics. Of course, there's everything else, right? We've seen gravitational wave. We haven't seen yet neutrinos, but we might see them, etc. Right? So for me, the most prominent, and of course the Haas and the TeV emission, there was, I'm sure there will be a full talk about that. The TeV emission in 19, what was that, 04 or something. But for me, in terms of statistics, I think the one that would provide the best, statistics, I would say, would be polarization, and I think that is very important. There is still, I want to remind you all that there was like 5 or 6 years ago, there was this elliptical polarization, circular polarization detection, which was never explained. No theory predicted any circular polarization, but it was seen at the level of a few percent.
In optical during the afterglow, you mean, right?
Yes. And nobody still, I heard several talks about that. Nobody had any explanation about it. I remember myself, I was thinking a little bit about that. I could not come up with anything convincing, and I just moved on. But for me, the next big step, if you look like 5 or 10 years from now, I think this would take, heavier weight.
But then you would need to have multiple measurements in polarization to again differentiate between weather and climate here.
Yeah, well, Polar 2 is going, I mean, we're building it right now. It goes up in 3 years. It's basically 4 times as big as Polar. And we already got pretty good measurements with Polar. We just basically need more effective area. And if everything scales the same way, we're going to get several really nice measurements of polarization from 10 keV to an MeV or so. And that's being built and flies in 3 years. So yeah, that's probably the next future. But of course, we need good predictions for polarization. I mean, this was the difficult thing with those observations, is that we've been hearing for quite some time that polarization will break all the degeneracies. And we got time resolved simultaneous spectral polarization measurements with Polar. But then we find there's no really good models to explain the evolution of the polarization angle, for example. So there needs to be, those need to be ready, because those observations will come pretty soon.
Thanks, Michael, for your comments. Actually, trying to bring a little bit closer to the topic of our session, maybe if I may ask you, everyone, maybe your considerations about this recent trend in the observation, namely that you have very strong spectral evolution even during the single pulse. I'm not talking about the burst itself, but single pulse evolution. A lot of data with this. What is your feeling about this? Is this indication of some really physical processes in the source, or is this still related to hydrodynamics of the flow, or whatever? What do you think about?
I mean, I think that's actually the key right now. I mean, Damien and I wrote this one paper, which I half believe, on the external shock. This was the only really nice analytic model back from Chuck's days, where you can fit the evolution of E peak along with the spectrum and stuff like this, and you have everything. You have the spectral predictions at all times and wavelengths, and does it work? I mean, for this one burst, yes, it doesn't really. I never really found something else that looked like that. But that's kind of where we are now. We're now fitting physical models, but especially in the photospheric regime, we need predictions for the temporal evolution. We do see a very specific evolution of E peak. It seems to fall as a power law, T to the -1, something like that. And it looks like a trend across a lot of GRBs, but you need to be able to match that with the spectral evolution with the spectra. And if that's probably what will end up breaking the degeneracies between models, as well as having polarization.
I like this point very much. Asaf, what do you think about this thermal evolution that you were finding with the Reed, right? With early on with the sweep data, and then later on with Fermi. This thermal evolution, I mean the temperature evolution, was I think remained never explained, no? From basic principles.
It was explained partially.
Partially, right.
we did manage to get some explanation. Whether it's convincing or not, I don't know. Personally, I actually agree with this statement. You know, there's always an easy answer, right, which is to put everything into the central engine. Absolutely. But for me, this is basically saying, right, so okay, so the central engine does what it wants, unless you have a very convincing model for how the central engine should behave. Otherwise, you know, it's just saying, it's much more interesting to come up with something which is more natural and can have, you know, have predictivity, put it other ways. So something which you can associate with some physical mechanism that you may understand, or with some geometrical effect that you may understand. That was back what we were trying to explain, I think with some success, is a structure of the jet, to say, okay, you know, we can attribute this evolution to you know, the structure of the jet, essentially, to the fact that we might be seeing photons coming from different regions of the jet in different times. Again, this works partially. I agree with the general assessment that Michael said, that essentially we have, and that's why I'm optimistic, besides that I'm generally optimistic in my nature. We do have a lot of information with both spectral information and temporal information. When we combine them both, this should give us enough, you know, enough information to really decipher what's going on there. So yeah, I mean, this is, you know, you start with some correlations, which is always good as a starting point. I mean, you cannot take it too seriously, because at the end, that will prevent you from having a physical model, which is always more, not always, but can be more complicated. But it's a good starting point. This is, you know, this is a piece of information which you need to take into account. Same might be a Matthew relation or something. You know it's there. Now we need to find some convincing explanation to it. So yeah, so this type of correlation, for me, this falls in the same category. We know it's there. Now we just need to find some convincing explanation for it.
Well, yes, I like your optimism as well, actually. Let's hope, yes, because eventually, when you mentioned Zvi, you know, of course, he's probably the veteran in this field, and this is psychological effect that when you are putting so much effort in this, you know, in some work, and then after all, you see that you didn't reach quite your goals, probably. I mean, it's just psychological feeling that he ended up like this. But we are still optimists. We are still young.
I am.
Okay, I am not sure. Well, if anybody else would like to add any consideration, probably we can. It's quite late already. We can eventually postpone some additional short discussion to the end of the second part of our session tomorrow, if you don't mind. Is okay?
Yeah. So tomorrow there are many more speakers actually, so the timing might be a little bit more difficult for discussion, but I guess at the end we can still take 15-20 minutes for.
Yeah, we can allow for that. Yes, sure. Okay, thank you everyone for contributing with talks, with your ideas, and see you tomorrow.
Thank you, everybody.
Thank you.
Have a nice evening. Bye.
Bye-bye. Okay.